Good grief. Intra says right on the board. Guys, read it. Look.
My finger.
If you'd come to class prepared, you wouldn't have to disrupt class. Intraplate activity. Fowler, come, you know what, stand up, walk over, and get it from her if you want to borrow it. No,
Ooh.
let him come to you.
Ooh.
All right. Shh.
Listen to him.
Intraplate, guys, intraplate activity is inside a plate. Like, not at the boundaries, inside the boundaries of the plate. Okay? That's what that means. You need to figure it out. What do you need? Oh, look at that. It's right here. Just come sit over here. Shh. Come sit right here.
Pardon interruption. Teachers, please make sure you post attendance before releasing any students. At this time, criminal justice students to the library, please. Criminal justice students to the library once you posted attendance. Thank you.
All right, so intraplate means inside the plate. Interplate would be at the boundaries, right? This lesson is about intraplate, so inside the plate boundaries, geological activity. We've got two pictures there. The one on the left is?
Lava.
It's lava. And so you can see the inside's molten. It's starting to crust over, right? It's cooling down. What?
Did you say intro was inside?
Intro, like inside of the borders. We're not at the boundaries of the plates. We're well inside. Okay, but there still can be geological activity. What's this picture of, do you think? A geyser? And where do you think that might be? Looking at the picture with the background, what? It's probably Yellowstone. In fact, it tells us. But if you look back here, you can actually see the higher point, which is kind of the rim of the caldera. And we'll talk about that here in a minute. The cool yellow colors, that's from the different bacteria that live in it, the chemicals. And then, yeah, you've got the geyser spewing. Anybody been there?
No.
That's fine. When I was your age, I'd never been there either. I didn't go anywhere until I was in the military. Why does some geological activity take place away from plate boundaries? Because most of it happens at the plate boundaries, right? At the divergent, the convergent, the transform boundaries. But you can still have activity going on in the center of a plate if, usually, it's the result of a hot spot. So if you don't already have this in your notes, you probably do from when we talked about Iceland. A hot spot, if you don't recall, is a plume. A plume, by the way, is a column of superheated material. So that heat energy carried to a relatively small point on Earth's crust can do what to the crust? We've got a column of superheated material.
Eat it.
Melt it, right? It's going to heat that section of crust up so much it'll melt, meaning you can have volcanic activity there, right? Cool. Two hot spots that we're going to talk about today are Hawaii and Yellowstone. Hawaii, oceanic crust, Yellowstone, continental crust, okay? Starting with, well, let's read this. It says most geological activity takes place at plate boundaries, but some activity does not. Much of this intraplate activity is found at hot spots. Hot spots are plumes of hot material that rise through the mantle. Hotspot volcanoes erupt when hot material melts to create magma. If you've got a pen and you like to click it, oh my gosh, every day, every day. In fact, you know what? You're no longer allowed to have pens. You should have an old school pencil. You're fine today, but try not to click it.
Hey, take the hood off too.
That's like your tick. That's your tick, isn't it? Hey, Nelson, why don't we not worry about other people? All right. Shh. Many hotspots appear to be fixed in the mantle. What does that mean, fixed?
Don't move.
It means it was broken and now it's fixed? No, it means what?
It don't move.
It doesn't move. It is stationary. Not the kind of stationary you write on with your clickety pen, right? What are you guys looking at on your computers? You're not doing the questions, are you?
No.
You're just reading along?
Yeah.
Okay.
That's a lot.
Last period I had two. They're like, oh, we're done. I'm like, we didn't even finish. Oh, we're done. We clickety clacked through. Could you try? Could you try not to make noise
I
constantly?
dropped.
Yes, I know you did.
Don't
We
drop
heard it. We all heard it.
Yeah.
All right.
I think she's frozen.
This means if they're fixed, that means that they do not move relative to each other, but the plates do or do not move.
Don't.
Dude.
They do. The plates are moving. Pay attention. We're talking about plate tectonics here. They move. So it's useful to scientists because if they've got something that they know is stationary, they can track how much the plates move relative to the what? The thing that's stationary, which is what?
On the plate.
The hotspot.
The hot spot. Thank you. The plate's moving relative to the
Hotspot.
hot spot. Hot spots in the oceans. Chain of volcanoes form as oceanic plate moves over a hot spot. This is how it happens. A volcano forms over the hot spot. But the plate is what? Moving. Here's your plate. Here's your hot spot. Boom, it punches through with a volcano. Okay? The plate's still moving. Boom, it punches through with another volcano. Plate's still moving. Boom, it punches through with another volcano. What would that form in the ocean if the volcanoes reached the surface?
Explosion.
Islands. Volcanic islands. Yeah, it could be explosive. Most of those, though, aren't as explosive. At least the Hawaiian ones we're going to talk about. They're a little more gentle because the lava is more fluid. It's not as chunky or sticky. Okay. Yeah, since the plate's moving, the volcano moves off the hotspot. When the hotspot erupts again, a new volcano forms over it. This volcano is next to the first one. And then it happens again and again. You end up with a chain like this. So here's an image of the Hawaiian island chain. The biggest one is the newest. It's still growing. This is where the active volcanism is for the Hawaiian hotspot. As the plate moves off, the arrow showing the direction that it's moving, the islands that it made in the past start to what?
Erode.
They start to erode. They're not going to expand. They're not being added to. They're off the hot spot. They start to erode. Also, think about this. That superheated material, when a fluid, like magma, because it can act like a fluid, is heated, it becomes more dense or less dense? Less dense. So it pushes up, yes? Think about the crust. If you've got something pushing up on it, what would it make on the ocean floor? A high spot, right? It's shoving the whole ocean crust up at the hot spot, and then the island pops up. As the plate moves off of that hot spot, it goes where? Down to where the ocean crust is lower relative to where it was high with the hot spot. So not only is the island eroding, that's true, but it's also just moving down as the plate comes off of the hot spot. Does that make sense? So when we're looking at these islands, they move down off of that hot spot, they subside, and they erode away. So if we look at Google Earth, and we find the Hawaiian island chain, we say, okay, there is the Hawaiian island chain. Sure enough, we've got the largest one here. It's sitting on top of the hot spot. As the plate moves off, those islands subside and erode away. But check it out. It continues to happen to the point that all of them are beneath the waves. Now, there are some exceptions to that. You've got some that were big enough that they are still above, but just barely. So if that's the case, where we have this rim, guys, this is a volcanic, it's a caldera. Do you guys know what a caldera is? Put it in your notes then. If you don't know what it is, it's a new word then. Caldera, C-A-L-D-E-A, D-E-R-A. Can I erase this? This is like days old. A caldera. Put it in your notes. It is a volcanic what? What's it look like?
Island.
It's a volcanic crater. This is the top of a volcano. It tapers off in those directions. This is the part that's just barely exposed above the rays. You got this ring, that is the rim of the caldera. And then you have the center of it there. And usually when you see these atolls, it'll be a rim and one side is just higher than the other. That's because as the volcano grows, usually the vents, the main vents, are slightly offset. Does that make sense? It's not erupting directly out the top. It's slightly offset. So you'll have one side that ends up higher. So for Midway, it's perfect, guys. For naval activity, it's perfect because you can come in the shallow end where the rim is actually below water, and then you're kind of protected, aren't you, from wave action and things like that. And then you have a little bit of land usually that you could put some buildings on, maybe a runway, like in this case you've got the Midway runway here, actually two. Got a runway over here, the Marines are there, and then we have another base over here. Okay? Questions on that? If you're a World War II history buff, I'm sure you know all about Midway. All right, back to the, oh wait, no, we're not done yet. So if we keep going to the northwest, we're going backward in time to these islands that some of them may have been above the waves in the past. And if we zoom out, you can track back. It's like footsteps. It's like tracks from this hot spot. And it shows where it had been. It also shows, guys, look at this. What is going on right here? It turned. What turned? What changed? The direction the plate was moving. So these older seamounts were formed when the plate was moving north. Since about this point, it's been moving west. You guys see that? So they're tracks. They're hotspot tracks. Now, if we look at Yellowstone, where we were looking, you'll actually, it's much harder to see, but where Yellowstone is now, this hot spot used to be further off to the west as well. Okay? Kind of neat. They're not in the same spot. They do move relative to the crust, or rather, we should say the crust moves relative to the stationary hot spots, right? Okay. Moving on. Talks about Kilauea. Is the most active volcano there. There are others, but they're all fed by that same hot spot's energy. This is about what we just looked at. Read along with me. It says the Hawaiian Emperor chain of volcanoes formed over the Hawaiian hotspot, the Hawaiian Islands formed most recently. Kilauea volcano is currently erupting. It's over the hotspot. The Emperor seamounts are so old, they are no longer above sea level. The oldest existing seamounts are doing what now? They says they are, they're look, you trace them, they're going to this. What's this feature again? The blue, darkest blue is the deepest water. So these are trenches. The Pacific plate is subducting beneath the North American plate and the Asian plate. Okay? So as it does that, these remnants of islands or seamounts are getting what? Nom 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 nom. Right? They're getting eaten up by the trench. They're getting recycled. Could we send some sort of submersible and retrieve crust, rock from these old seamounts? Could we use absolute dating techniques, radiometric dating techniques, which we'll learn about here in a few weeks, and determine the age of those islands? Sure. At that point, we would know, okay, the thing that created those islands or seamounts was still around back then, which was what? What was creating those seamounts? The same thing that's creating the Hawaiian Islands now. What is that? The hot spot. So we know that was around all the way back to when these were formed. Now, could we assume that there's probably more that have already subducted? But for how long, we don't know because the evidence is destroyed. It's gone. So therefore, we only know for sure that the hot spot has been around as long as these last seamounts are still there. We don't know. At some point, hot spots do come and go. They do cease to exist. Okay? We don't know why or how. That's still a mystery to scientists, as far as I know. Unless some major discovery has taken place since I did my learning. Okay. Back to the reading. Pollution chain, subducting, All right, so now we're talking about hot spots over continents, or under continents. This is the Yellowstone caldera. A caldera, again, is a what? A volcanic crater. So if you look at Yellowstone, let's go back to our Google Earth. If you go to Yellowstone and you zoom in, can you see a volcano here? But can't you? Can't you? Guys, the actual lake at Yellowstone is the depressed volcanic crater. But it's so huge that it doesn't look like what we have in our mind as like a stratovolcano or a cone volcano. It doesn't look like that. It doesn't look like a shield volcano because it's got this big old drop off in the center. Okay? Guys, do you see these like little ripple mountains around here? Mm-hmm. This is the rim. That's the rim. This whole center portion blew out, throwing debris up on the rim. And then all these little ripples and stuff in here where it's started to erode since that last eruption. Okay? This thing is monstrous. It is huge. That's why they call it a what? Super volcano. Okay? It's big, guys. That's what I'm saying. That's what I'm trying to say. Scrolling down. Hot spots are also found on the continental crust. Could you at least turn around and pretend you're paying attention? Could you? Maybe go to the other side, sit on the other side so you're like facing the right direction. Same thing with you over here. Like not even facing the right. I mean, you can at least turn. She's okay. Since it's more difficult for magma to make it fit through the thicker continental crust, they say that they're they're less common. So they're saying hot spots over continental crust are less common because it's thicker. It's harder for it to get all the way through. Does that make sense? It's got more to melt through to make it to the surface. That makes sense to me. However, there's another kind of simpler reason why there's fewer hot spots under continental crust than oceanic crust. Can anybody think for a second why that might be? Why would there be more hot spots other than the whole idea that the continental crust is thicker, so it's got further to melt through? Why would there be so many more in oceanic crust than continental? Yes?
Because closer to it?
Closer to the surface?
Yes.
So that hot spot would be closer to the surface? Right, because it's thinner. Right, so oceanic crust is thinner. Okay, so other than that, though, which is there more of? Oceanic crust or continental crust? There's a lot more oceanic crust on planet Earth. So statistically, if the distribution of hotspots around the globe were kind of random and even, wouldn't it just be statistically true that there'd be more chance that they would come up through oceanic crust? So that plus the fact that you got to melt through a thicker crust, that's why we see more hotspot volcanic activity on ocean crust than on continental crust. It says it's not as common, but we have an exception at Yellowstone. This hotspot is very active in the past. It's produced enormous, right, super volcanic eruptions. Now its activity is best seen in the geysers. If you don't know what a geyser is, you can write that down. So you got water gets in through the gaps. There's chambers that the water can trickle down into, and it's close to that really hot rock. So it boils it back off and shoots it out under pressure. Cool. Summary. Not all geologic activity is found at plate boundaries. Make sure you're checking this against your notes. You should have at least an understanding in here or on your notes. Activity within any plate is called intraplate activity. Most intraplate activity occurs at hot spots. Guys, if you pay attention to this summary, you'll get most of the questions, and yet I've had people getting them wrong because they're just clickety-clacking until they get it right by accident. That's sad but true. Hotspot volcanoes erupt mostly on oceanic crust. Few hotspots erupt on continental crust. The difference is due to the thickness of the crust and the fact that there's simply more oceanic crust than continental crust. Hotspots can be used to tell the speed and direction of the plate movement. Questions, comments, concerns on any of that? I'm going to play this video, but a reminder, it's not going to, you just can't stop from making noise. This won't go full screen, so feel free to rewatch it on your full screen. And then I'll assign the questions for you, okay? Nope, no, I don't want to go to the next video. Go back. Nope.
A few hundred years ago, scientists believed that volcanoes were burning mountains of fire. Today, we know they're really openings or vents to the hot interior of the planet. About 1,500 volcanoes around the world are classified as active. Nearly 90% of these rest in the Ring of Fire, a band circling the Pacific Ocean. Their location is no accident. While the Earth's surface looks stable, its crust is made up of immense slabs of rock, like puzzle pieces that constantly shift. Where these tectonic plates interact, volcanoes often form. Friction from shifting plates melts the Earth's crust, causing rock beneath the crust to liquefy. This molten rock, or magma, then becomes a volcano by erupting through rifts in the plates. Once magma escapes from the Earth, it's called lava. But not all lava is the same. Running lava flows quickly and forms the gentle slopes of shield volcanoes. Thick, sticky lava doesn't flow as far and tends to form the steeper slopes of composite volcanoes. Composite volcanoes can erupt violently, hurling ash and lava at speeds up to 200 miles per hour. These eruptions sometimes blow away large chunks of the volcano itself. Some volcanoes, like Hawaii's Kilauea, form over
Did you see that caldera?
crust, where magma rises in the middle of a tectonic plate. Hawaii's Kilauea, the volcano.
All right here. That's a volcano mountain, and the rim right here. You guys see the rim of that mountain? That's your caldera. And notice one side is higher because the explosion is off to one side. It's usually not centered right on top. Okay, so because it's slightly off center on the mountain, you have this crater slightly off center. If this were an island, as it comes down off of the hot spot, the water's going to rise up, exposing just the rim and then the high end. That forms the atoll, like Midway Atoll. Does that make sense? Okay.
Chunks of the volcano itself. Some volcanoes, like Hawaii's Kilauea, form over hot spots in the Earth's crust, where magma rises in the middle of a tectonic plate. Kilauea is one of the most active volcanoes on the planet, and has erupted continuously since
Blue lava?
1983. Because Kilauea is a shield volcano, this constant eruption is a gentle one. Lava oozing from Kilauea constantly hardens into new rain, making Hawaii the only state that's still growing. Living near a volcano can be hazardous, as the residents of Pompeii learned in the year 79 AD, when Mount Vesuvius erupted, spewing superheated ash, poisonous gas, and rocks. This deadly combination, called a pyroclastic flow, is far more dangerous than a lava flow. Vesuvius buried Pompeii, claiming the lives of 2,000 people. Though volcanoes can be deadly, they also provide benefits. Volcanoes created 80% of the Earth's surface, as well as much of the air we breathe today. Volcanoes create rich soil for farming, and many countries harness their subsurface heat to create geothermal energy. Both creators and destroyers, volcanoes prove that beneath its calm surface, Earth remains a living planet, and a restless one.
Cool. All right, I'm going to assign this to you guys. I want you to be quiet as you work individually because it's an individual assignment. Does that make sense? You don't need to be staring at other people's screens. You don't need to be talking. You don't need to be updating on somebody while you're moving. Just shh. Also, I'm going to be talking at you about tomorrow. So you're now assigned. You can open it, but keep your ears peeled, okay? So tomorrow, if you've had your head buried in the sand or the snowbank, probably I am not the official that makes the decision. I'm just saying, if I rub my two brain cells together, I'm thinking we might have an NTI day tomorrow, right? They've warned us. If that's the case, I'm giving you this. It is a 10-question accompaniment to a documentary about Yellowstone that I will assign for you guys to watch tomorrow. What are you going to do tomorrow? You're going to watch a documentary that I'm going to post for you in the morning, and you will answer these 10 questions. If you lose this, that's fine. It's okay. You might prefer to answer on here as you're watching, and then when you're done, you could open up the digital copy that I'm going to have for you and just highlight the answers and then submit. Does that make sense? Or you can take a picture of this as long as I can make it out. You can take a picture of this and post that picture as your response as well. Does that make sense? If we have NTI tomorrow, this is due tomorrow. In other words, it's an NTI day. You need to do the NTI. It's still instruction. It's still a day that counts toward our year. That means it's not optional. Does that make sense?
What if it's not NTI?
Then we'll be here.
No, but like.
Oh, if they just call it snow, they won't. They don't want to push back graduation anymore. So if they can do NTI, they will. Now, based on what our superintendent has been doing and what he has been telling us, he's okay doing maybe 1 or 2 NTI days back to back. But beyond that, then that's when he would do a traditional snow day. Because it's not that difficult for us to give you something to do like for 1 or 2 days. But beyond that, like, we're not getting much educational benefit. Does that make sense? Like, I can send you home, and the documentary you're going to watch tomorrow and the questions you're going to answer help. They're a great extension to the reading from today. But much beyond that, I mean, I might be able to. I could throw another worksheet at you, or I could throw a documentary on the Hawaiian Islands at you. But I don't like giving new content on an NTI day because we're not together. Make sense? Okay, let me pass this out to you.